So we do need to understand a little bit of physics. All sciences are intertangled with each other, right? There's no hard line between physics and chemistry. So light, we need to understand the nature of light. So light is a form of electromagnetic radiation. And this is composed of perpendicular, meaning at right angles to each other, oscillating waves. One is the electric field, electro, and one is the magnetic field. So what is an electric field or magnetic field? It's a region in which an electrically charged particle would experience a force. Magnetic field is where a magnetized particle experiences a force. So you know, we've all played with magnets, right? So you know that if you bring two magnets together, North Pole to North Pole, they're going to resist each other. You can try to push them together, but they just don't want to go together. That's the magnetic force that's holding them apart, okay? These electromagnetic waves are moving through space, and they travel at a constant speed. It's called the speed of light. It's the speed at which light moves, right? So that's 3 times 10 to the 8th meters per second. And you don't really get an idea of how fast that is. So it's actually 186,000 miles per second, which is fast enough to circle the Earth 7 times in 1 second. I mean, you'd be hard-pressed to move your hand that fast around a globe, right? This is super fast. So here is an illustration of the electromagnetic radiation. So here we're representing the electric field component. So it's going up and down, it's oscillating. And then perpendicular to that, we have the magnetic field oscillating. Light and sound do not travel at the same speed. Light travels at the speed of light, right? And sound travels much more slowly, around 340 meters per second, instead of 3 times 10 to the 8th meters per second. Yeah, question? Is there anything that can disrupt the speed of light? Not in my world. But I know that, like, if an object gets close to the speed of light, then all sorts of things start to go wonky, right? And there's stuff about, time and space bending and all that kind of stuff. And I leave that up to the theoretical physicists, because it's cool and all, but it makes my head hurt. Yeah. So here we have a picture of a lightning strike, and that makes a big clap of thunder. It makes a really loud sound. If you were at this building that got struck, you would hear the sound at the same time that you see the light. But thankfully, we are not usually where the lightning is striking, right? So here's this person over here looking at the lightning. You see the lightning hit, and then seconds later, you hear the sound. And that's because the light travels to your eyes at the speed of light, 3 times 10 to the 8th meters per second, but the sound takes significantly longer to get to you. And so I don't remember what it is, but there's this rule of thumb. You can count the seconds between the flash and the crash, and you can estimate how far away the lightning strike was from you. And that's true. You can, because of the difference in the speeds. So waves in general have some characteristics. So here we have a wave, and we can talk about its amplitude, how tall the wave is. We can talk about the wavelength, which is the distance from one peak to the next peak. So this is called a peak, and this is a trough. We can also call this a crest. And so measuring the amplitude of the light tells us how bright the light is. The wavelength is related to the color that we observe. So here are 3 different wavelengths of light. So the distance between crests for this one is longer than that one, and then C is the shortest one. So our eyes detect this as different colors. Here we're looking at differences in amplitude. This would be a dim light. The crests are not very tall. And this would be a bright light. The crests are taller. So frequency is the number of waves that pass a point in a given period of time. So it's the number of waves or the number of cycles of the wave. And so units of frequency are hertz, capital HZ, or cycles per second. And both of those can be expressed as just s to the minus 1. So basically it's per second is the unit. The total energy of this wave is going to be proportional to the amplitude of the waves, how bright the light is, and to the frequency of the light. So larger the amplitude, the more force it has, the more frequently the waves strike, the more total force there is. So this is all very abstract. So this is not exactly how waves on the ocean look, but, kind of. And here's a chemistry student at the beach, right? So the waves come and crash on you. Which one's more likely to knock you over? A really tall wave or a really short wave? A tall one, because it has more energy, right? It can just literally knock you flat. Well, that's related to the amplitude. If the light has a larger amplitude, it has more energy. And then if you think about the waves coming in, so waves in the ocean, come in, I don't know, every minute or so, something like that. They're kind of steady, right? What if they could speed up? You could have them coming in slow, crash. Or they were coming in, bang, bang, bang. I mean, you wouldn't even be able to get back up, right? Higher frequency, more energy. Now, with light, it's always traveling at the same speed, and so the frequency depends on how close the waves are to each other, the wavelength. So the shorter the wavelength, the more frequently they will pass a given point. So wavelength and frequency are inversely proportional. If the wavelength is big, then the frequency is small. If the wavelength is short, the frequency is large. So this is a relationship. C is the speed of light, lambda is the wavelength, and this funny looking V here is the velocity. I'm sorry. That's new, and it's the frequency. Not confusing at all. We'll get to that. So the color of light is determined by the wavelength, which is related to the frequency. Right? So what we perceive as white light, like the lights overhead, the light that's coming out of them appears to be white, right? That's actually a mixture of all the colors in the visible spectrum. If you look at sunlight, it appears also to be white. It's got all the colors, right? If you pass white light through a prism, you cause these light waves to bend, and they're going to bend more depending on their wavelength. And so they'll get separated into individual colors. The violet light will bend the most, and the red light will bend the least. So the order here is always the same, and this is helpful to know. The order is red, orange, yellow, green, blue, indigo, violet. And the way I remember that is Roy G. Biv. Like, you know, it could be somebody's name, right? Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. Now, indigo is not a color that we normally find in our crayon box, but it's just in there between blue and violet. So when we perceive something to be a particular color, it's because that object is absorbing and reflecting different wavelengths of light. So if we look at this woman's shirt, it appears red because it's absorbing most of the light and it's reflecting the red light. And so what we see coming off the shirt is the red light. Her blue jeans are reflecting the blue light and absorbing most of the other colors. When we see something as black, like her hair, it's absorbing pretty much all the color. When we see something that's white, it's reflecting all the colors. Any questions? So there are some calculations that we can do with these numbers. A laser dazzles the audience in a rock concert by emitting green light with a wavelength of 515 nanometers. Calculate the frequency of the light. So they're giving us a wavelength, and they're asking us for frequency. So this is going to involve an equation. The frequency is equal to the speed of light divided by its wavelength. So this is the Greek letter lambda, lowercase l, and it looks a lot like a Y that got flipped on its head. This is the Greek letter nu, which is easily confused with an italicized V. But this is frequency. So we're told what the wavelength is. So the wavelength is 515 nanometers. And c, the speed of light, we can go look up, and that's 3.00 times 10 to the 8th meters per second. So if we put these numbers into this equation, okay, we've got the speed of light and the wavelength in the right place. Are those units going to cancel out and give us per second? No, because I've got meters on the top and I've got nanometers on the bottom. But here's where we can pull that little shortcut trick. Nano means 10 to the minus 9. Nano meters. And so we can convert that real fast. So 3 times 10 to the 8th divided by 515 times 10 to the minus 9. And this should have 3 sig figs, so 5.8. 3 times 10 to the 14th per second. You could write that as 1 over second. You could call that hertz. So that laser, the little crests in its wave, past a given point 5.83 times 10 to the 14th times in a second. Well, that's because the light is moving incredibly fast, and these are really, really small distances between those waves. Any questions? So we talked about how a white light contains a spectrum of colors, right? Visible light is only part of the entire electromagnetic spectrum. It's the part that we can see, the part that's visible. If we look at electromagnetic radiation that has shorter wavelengths or higher frequencies, those go together, this is going to have higher energy. So radio waves are the ones with the lowest energy, so they've got long wavelengths, low frequency. Gamma rays have the highest energy. High energy electromagnetic radiation is, I want my apples. Oh, so good. High energy electromagnetic radiation is dangerous. It can damage biological molecules. It can knock electrons off and turn your molecules into ions, and then they don't do the same reactions in your body, and it causes all kinds of problems. So that's called ionizing radiation because it makes ions. Okay, so here is the electromagnetic spectrum. This is an illustration from your book. So up here, we're showing frequency going from around 10 to the 4th per second up to 10 to the 24th per second. This line here is showing wavelength in meters. So 10 to the 5th, so we get 1 meter right in here, all the way down to 10 to the minus 15. So down here at the low wavelength, high frequency end, we have gamma rays, and then there's X-rays and ultraviolet. And right here in this little teeny tiny part here is the visible light. And they took this and they blew this part up. So this part right here all came from that, right? They just zoomed in on it because this is the part we're usually most interested in, the part with the colors. And so we can look at this and see that, well, green light's probably going to be about 530 nanometers, something like that. If we had, 450 nanometers of light, that would be blue. We can see that. This here does not correspond with gamma rays and a 10 to the 24th frequency. Okay? This belongs over here. So sometimes students misread this, and there's a particular question on a particular lab that they get wrong because of that. So I'm just warning you about that. It's helpful to be able to put these things in order. And so if you remember Roy G. Biv, there's our red, orange, yellow, green, blue, indigo, violet, right? And so we write that out, and then which one has the most energy? Well, what do you know about ultraviolet radiation? It's bad for you. It can give you a sunburn, right? But the light from these lights doesn't give us a sunburn because this is lower energy. Ultraviolet light has higher energy. It can burn your skin. So this is the high energy end because ultraviolet is next to violet, right? It's beyond violet. Over here on the other side of red, we have infrared, below red. So if you've ever seen a heat lamp, maybe like for a reptile, or you go to one of those hotels and they got this heat lamp on the ceiling and you turn it on and you're like, what's this? It's kind of a little bit of a red light, but it gives out a lot of heat. So the infrared light is giving off radiation in this area here, and a little bit of that is going to be visible to us as red, but most of it is the heat. That's not going to give you a sunburn. And so going higher in energy, the ultraviolet, that'll give you a sunburn. X-rays, well, those we use, right, to find out if you've got a broken bone or cavities or whatever, but you don't want too many of those, right? So those are more energy than the ultraviolet. The gamma rays are the really dangerous ones. They're out in the end. So over here, infrared, microwave, and then we get into radio waves. The radio signal that your car radio picks up, if you still have one of those, is the same kind of electromagnetic radiation as light. It just has a different wavelength and frequency. It's kind of crazy to think about. And you might wonder why microwaves are in here. We know that a microwave can heat food up pretty fast, but if you shine regular visible light on it, nothing heats up, right? Well, why are microwaves lower in energy? Do you want to know how a microwave oven works? Yeah. So microwaves have a frequency that corresponds to the frequency, well, let me say it this way. The bond, hydrogen-oxygen bond in water molecules responds to a frequency of light, such as microwaves, by moving faster. So it's the water molecules in your food that are absorbing the microwave energy and getting hotter and hotter and hotter. If you're trying to heat something up that doesn't have any water in it, it's not going to heat up very well, right? And you could end up like burning out your microwave or something. Any questions about microwaves? I don't think wearing foil on your head while you microwave is a good idea. So a prism can be used to separate light. It separates it by its wavelength. So again, we have those same colors, Rho G Biv. We get the white light coming in, and we see a continuous spectrum. We see all the colors in there. Right? Infrared light. So I said this is related to heat. A heat lamp gives off infrared radiation, which causes us to get warmer. And a lot of times you can kind of see a reddish glow. Well, infrared light can also be used for night vision, right? Night vision goggles, stuff like that. How does that work? Well, it's actually thermal imaging, because the heat that a living object gives off is infrared radiation. Our eyes can't detect that, but we can develop sensors, cameras, that can detect that. So this is from a field trip I went on with my daughter, and they had this infrared camera. So this is visible light camera, and this is the infrared camera. And you can see my phone was pretty warm because I'd been taking lots and lots of pictures. But you see where our skin is? It's red, and then our clothing and our hair, it's not as red. And then in the background, it's cooler because there's not infrared radiation being given off, the heat. So the night vision is seeing heat, basically. So, you've got somebody running from whoever trying to get away, and they're hiding in the woods. Well, if you have night vision, you can see their heat signature, right? So that's when you want one of those like space blanket things. You could hide under that, and that would stop it. I didn't say that. The really high radiation is dangerous, but it can be used for good. So radiation therapy is often used to kill cancer cells. The problem with that is, so say you have a tumor inside your brain, inside healthy tissue, how do you get radiation to the tumor without also damaging the healthy tissue around it? And so a really cool technique is to rotate the beam. So the beam moves around, so it's always hitting the tumor, but each time it's going through a different part of healthy tissue. So the healthy tissue is getting a very low dose of radiation, and the tumor is really getting hit, literally from all sides. And so in that way you can cause the tumor to die without doing too much damage to the tissue around it. there's a section in your textbook where it talks about the different types of radiation. I just talked about a couple of them here. I would encourage you to read that. It's just good to know. Waves can interact with each other, and that interaction is called interference. So they can do this constructively or destructively. If we have two waves that are in phase, meaning that their crests are lined up and their troughs are lined up, then those will reinforce each other and the amplitude of the interaction will be greater. If we have out of phase where it's crest lined up with trough, then they will cancel each other out. It's a destructive interference, and it can actually go to absolutely zero. This is the technique or the technology used in your fancy AirPods, right? With the noise canceling. Ever wonder how they do that? They take the sound around you and they shift it just a smidge and send it into your ear along with the sound coming from outside. And because it's shifted enough that it's out of phase, they cancel each other out. It's crazy. It's crazy. I don't know if you've ever played on a trampoline. Some funny things can happen when two people are on a trampoline, right? Depending on when you're bouncing and when you're landing. Occasionally you come down and you were expecting to bounce back up and nothing happens. You just like stop dead. That's because you got some destructive interference from the other person. And other times you go like shooting in the air and hopefully you don't fall off and break your leg. Constructive interference of the waves between the people. Any questions? Diffraction is a thing that waves can do when they encounter an obstacle. So when waves encounter an obstacle or an opening in a barrier, they will bend around it. Traveling particles do not diffract. Traveling particles travel in straight lines like particles are supposed to. But light is an electromagnetic radiation, and it can diffract and cause interference patterns that we can observe. So an interference pattern is a characteristic of all light waves, but particles do not do that. So here are wave crests coming to a barrier that has a slit in it. And as the waves hit, the part that goes through gets bent. This is called diffraction. And you could play with water in your bathtub and make little ripples and put things in the way and try to get this to happen. So that's what waves do. They bend like this. If you have particles traveling in straight lines, they either hit the barrier and bounce off or stop, or they go through and they keep going straight. So we can look at what happens around this barrier with a slit, and that can tell us, is this a wave or a particle? So there's a very famous experiment called the double slit experiment. Here's an illustration of it, and then I've got a video. So here we have two slits, and we've got a single light source. So the light coming from this source is all, of course, in phase with itself, right? So as it hits this slit and as it hits that slit, it's in phase. It goes through here and it is diffracted. And over here, it's diffracted. And as these diffracted waves spread out, they begin to run into each other and interfere with each other. And what we see is regions where they destructively interfere. We see that as dark spots on the film. And then we see bright spots where the waves are in phase and make the light brighter.
What is light?
What is light? What is light? That's a good question, isn't it? What is light?
Isn't it an element?
Light is brightness, I guess.
We have auras,
We all have auras.
which are light.
Yes, they are.
It lights up the room. It makes it not dark.
What's the difference between blue light and red light?
The colour.
It goes in your eyes and then you see stuff.
They range from white to red to orange to green. It's like the chakras of your body.
Can you see my aura?
No, not particularly right now.
Is it too bright out?
It's very sunny out here today.
Does that make it harder to see someone's aura?
Not necessarily.
If I was to explain it to a blind person, right,
Yeah.
it would be the difference. You see nothing whatsoever as a blind person, whereas I see things in front of me.
To be fair, the question of what light is not an easy one. For centuries, the greatest minds in science debated this issue. In the late 1600s, Newton proposed that light was a stream of particles, or corpuscles. He proposed this in his treatise Optics. But at the same time, a Dutch physicist named Huygens proposed that light was a wave. And this debate raged on until it was settled by the experiment I've recreated today. Thomas Young's double-slit experiment. To make sure I got the experiment right, I went to the original source. With the help of Brady Heron, I managed to get into the vault underneath the Royal Society in London. There I found Thomas Young's handwritten notes from 1803.
I brought into the sunbeam a slip of a card, about 1/30th of an inch in breadth, and observed its shadow, either on the wall or on other cards held at different distances, besides the fringes of colors on each side of the shadow. The shadow itself was divided by similar parallel fringes, smaller dimensions. Wow.
This is an experiment so simple that you could make it at home, and yet so fiddly that I have never seen it before done with sunlight.
I was thinking about doing it in a box, like a fridge box,
And you can take it out on the street.
taking it out on the street.
Could I possibly interview you guys for about a minute? We're doing a science experiment. I have here is an empty box. And this is a little eyepiece where we can look in, and this is a hole. And I'm going to place this slide above that hole. And if you look closely, you'll see that there's two openings. Very narrow openings side by side. It's a double slit. Now before we have a look, we need to tilt it towards the sun a little bit. So we want the sun to hit this double slit directly. What are we going to see on the bottom?
Well, the obvious thing you think you're going to see is you're going to see two lines.
2 lines on the bottom of the box, 2 bright bands.
Two little lines.
Yeah. I think it'll be one line instead of two.
I can expect to see the whole box lit up.
That'd probably be a kaleidoscope of some sort.
A bunch of colors.
Probably, yeah.
Rainbow, different colours.
There, have a look. You expected to see kind of one line. Is that what you see?
No.
I see dots.
How many?
It's one circle.
Oh, there's one in the middle strongest, two either side.
The two on the outside are multicolored, and the one in the middle is just white.
Kind of a rainbow.
The rainbow of colour as well.
Quite a few colours and lots of little dots.
Like there are more dots appearing.
I think I can even see more dots spreading along. Yeah, that's amazing. Yeah, I can see tons of dots now. Not tons, but I can see dots spreading across that way.
Either side.
Yeah, definitely.
Isn't that amazing?
Yeah, that's incredible. And that's just nothing else apart from
Two slits.
two slits. That's incredible.
Well, all we're doing is we're putting a light through two very narrow slits side by side. So how does this make any sense?
There's some kind of principle involved there. The average person's not familiar with. That's the only explanation.
No, I'm really confused by it, but I'd like to find out why.
People were debating, is light a wave or is it made of particles?
So what causes that?
Well, if light were behaving as particles, you would expect them to go through each slit and just produce a bright spot underneath. So we would see two bright spots on the bottom of the box. But if light's behaving as waves, then the wave from one slit can interact with the waves from the other slit. I've got a demonstration here on a little pond where we can see this with water waves. I have two sources of ripples, which are basically like the two slits. When I create ripples with a single source, they travel out with circular wavefronts. Nothing particularly surprising there. But if I add a second source of ripples, then we start getting an interesting pattern. See that? This pattern is created by the ripples from the two sources interacting with each other. Where they meet up peaks with peaks and troughs with troughs, the amplitude of the wave is increased. That's what we call constructive interference. But if the peak from one wave meets up with the trough from the other, then we get destructive interference, and there's basically no wave there. And this is exactly what was happening with the light. When the light from one slit met up, peaks with peaks and troughs with troughs, they constructively interfered and produced a bright spot. But if the trough from the wave from one slit met up with the peak of the wave from the other slit, they would destructively interfere, and you wouldn't see any light there. It's light cancelling itself out.
This is basically the same as like having 2 drops of water fall in a swimming pool.
That's
Get exactly the same
And then they
pattern.
go and overlap. As this ripple overlaps with those ripples,
Yeah.
down the bottom, you get a series of, you get like a bright spot, and then a dark spot, and then a bright spot, and then a dark spot, and then a bright spot. Now there's a slight complication, which is that sunlight is composed of many different colors, and they have different wavelengths. So obviously they're going to meet up at slightly different points. And that's what caused the rainbowing effects as we go further from the central maximum. So you saw the ones to the right were slightly colored.
Yeah,
That's
that's
because
working.
the reds are going to meet up at different places than the blues.
And that's all that makes the colour differences in different wavelengths.
Exactly.
That's amazing.
So the difference between red
So
and blue.
that red bin over there, the green part is just, I'm seeing
It's a
that,
different-
it's just different
different
wavelength. And that's how we bring in all these beautiful colours all around us.
Exactly.
That's amazing. I'm amazed. Oh, good on you, thanks, Ben.
Hey, thank you.
I have been enlightened. Literally.
Any questions? I really like this video because we can really see how, let's go back to work. So you can really see that this is the area where you're getting the destructive interference, these places where there's no wave, and then the wave here is bigger than the individual wave that was coming from either ball because they're constructively interfering. And so, let's see if this will work. If you had, a piece of paper here, then what you're going to see is you're going to see a bright spot here and a dark spot and a bright spot and a dark spot and a bright spot. So that'll show up as a pattern like this. Okay, so that demonstrates that light is a wave, right? It diffracts like this. Well, light also has a particle nature. So it was observed that many metals will emit electrons when a light is shined on their surface. It's called the photoelectric effect. And classic wave theory attributed this to light energy being transferred to the electron. And so, according to this theory, only the amplitude, the intensity of the light, would affect the emission of electrons. The idea would be that if a dim light was used, if you waited long enough, the energy would build up and the electrons would be ejected. There'd be a lag time. So this is an illustration of a photoelectric setup. So here we have the metal surface, and we've got a voltage across this with a positive charge over here, and the metal is a negative charge, and then we've put this in an a vacuum chamber, so that when these electrons get ejected, they're not going to run into molecules of air. They're just going to go until they reach this positive terminal. And the meter here can tell us how many electrons are coming through in a given period of time. So we shine a light on this. The light is going to hit the metal surface, and depending on what kind of light it is, electrons may or may not be emitted. So here is a graph showing the rate of electron ejection as a function of the frequency of light. So here we see at low frequencies of light, there's no electrons being ejected. It doesn't matter how long you wait. The low frequency of light will not eject any electrons. When you get right here, all of a sudden you start getting a whole bunch of electrons being ejected. That's called the threshold frequency. That's the minimum frequency necessary to eject electrons. There is a difference in intensity of light. If you have more intense light, then you get more electrons. And if you have lower light, dimmer light, you get less electrons. But you still get electrons. Below the threshold frequency, you don't get any electrons at all. So Einstein proposed that light energy was delivered to atoms in packets, or quanta. A quantum or a photon is a packet or a piece of light, a particle of light. So the energy of a photon, delta E, is directly proportional to its frequency, nu. I should have put these descriptions earlier. But that's nu, the frequency, is inversely proportional to the wavelength, lambda. And the proportionality constant is called Planck's constant, and it's 6.626 times 10 to the minus 34 joule seconds. You do not have to memorize that. The energy of this photon is equal to Planck's constant times the frequency, which is the same as Planck's constant times the speed of light divided by the wavelength. So we can do calculations with this. A 100-watt light bulb radiates energy at a rate of 100 joules per second. The watt, a unit of power, which is energy over time, is defined as a joule per second. So 100 watts is the same as 100 joules per second. If all the light emitted has a wavelength of 525 nanometers, how many photons are emitted per second? Assume 3 sig figs. So I'm just going to highlight the 100 joules per second because 100 watts is just another way of saying that. And then we have this wavelength, and this is telling us that we want to find how many photons are emitted per second. So this is a challenging problem, but it does just come down to units. So we've got a wavelength, 525 nanometers, and we know that we've got 100 joules per second, and we can calculate the energy of this light. The energy is Planck's constant times c divided by the wavelength. So this was given on the previous page, 6.626 times, I think that's right. Yeah. Times 10 to the negative 34 joule seconds. And then here we've got the speed of light, 3.00 times 10 to the 8th meters per second. And we're going to divide by the wavelength, 525 nanometers. Is nanometers a good unit for that? No, I've got meters up here. So I'm going to write times 10 to the minus 9 meters. And what's going to happen here is that my meters are going to cancel out, and my seconds are going to cancel out. So I'm calculating the energy in joules of one photon, one piece of light. .786 0.7863 times 10 to the minus 19th joules. In 1 second, we'll experience 100 joules, because it's 100 joules per second. The seconds cancel out. This number of joules is equal to the energy of 1 photon. So then we could use that and say, well, 1 photon has the energy 3.7863 times 10 to the minus 19 joules. .64 times 10 to the 20th photons per second, or photons in 1 second. Questions? Because this equation is the energy of a photon. So when you talk about the energy of the light, well, how much of the light? It's one piece of it, 1 photon. So being able to do calculations like that is nice, but it's not absolutely necessary. This is something you should be able to do, though. Arrange 3 colors of visible light, green, red, and blue, in order of increasing wavelength, frequency, and energy per photon. And I'm going to talk you through how you can do this without really memorizing anything. So I drew 2 waves. They're ugly waves. Best kind. This has a short wavelength, and this has a long wavelength. Which one has higher energy? Short. So this is high energy, and this is low energy. And they kind of look like that, don't they? This one's just bouncing up and down all over the place, and this one's like, right? Okay. So, long wavelength is low energy. I have to look at it because these things, and then the frequency and the wavelength are backwards, and so it just really gets all complicated, and that's why you need to write yourself some notes. Okay, so now we're going to write down Roy G. Biv. And what is next to the violet light? Is it infrared? No, it's ultraviolet, right? UV light. And what's over here next to the red? Infrared, IR. So this is the one that has enough energy to give you a sunburn. This end is high energy. So this way is high energy. Let's not get these mixed up together. So this end is high energy, and this end is low energy. So if we were looking at this one, energy per photon, we want in order of increasing energy. So that means I want the lowest energy first, then the middle one, then the highest energy. And I'm looking at red and green and blue. which is the lowest energy? Red. So red, and what's next? Green, and then blue. Was that hard? And draw your two weird waves, and the crazy one is higher in energy. And then you do Roy G. Biv. Ultraviolet is next to violet. That's the high energy end. So here's our order, just sitting in there. Now they also want wavelength and frequency. So we drew these pictures, right? And we saw that high energy is a short wavelength. This is the wavelength right here. So this is long wavelength at low energy. And short wavelength at high energy. So what's the order from low to high for the wavelength? It's going to be the opposite, right? Because this end is short and the other end. So it's exactly the opposite. It's going to be blue, green, red. And what about the frequency? Well, if you imagine a person standing here, or two people standing here, and these are coming at the same speed, who's going to get hit more frequently? The guy on the top, right? This guy's going to get hit more frequently. This is high frequency. So the high energy is high frequency, and the low energy is low frequency. So going from order of increasing, so low to high frequency will be the same order as for the energy. Red to green to blue. And for each of these, there's only two really possible choices. Because the green light is going to be between red and blue, no matter what parameter you're looking at. Any questions?
Red, green, and blue. I missed that.
Green, red, and blue. Because the question I didn't, yeah. No, it was a good question. I don't know why they picked those. Maybe those are their favorite colors. Okay, so those two examples kind of interrupted what we were talking about with the photoelectric effect. I really should move those slides. Yeah, it'll probably never happen. So back to the photoelectron effect. Photoelectric, we're shining light at this metal, and if it's a high enough frequency, a high enough energy, electrons come out. So if we have a photon that's right at the threshold frequency, it has just enough energy to dislodge a single electron. And so that's called the binding energy of the electron. That's symbolized by the Greek letter phi. If we have light that's higher frequency, higher energy, the electron is going to get more energy than it needs to escape. Right? So the excess energy that it has is going to be kinetic energy. So we can say that the kinetic energy of that electron is the energy that the photon had minus the energy of the binding. Okay, so this kind of reverses entering and exiting, but I think it's happier than the alternative I just thought up of, which is escaping from captivity. We don't want to go there. We're going to go to Disneyland instead. So let's think about going to Disneyland. I think of electrons as being like little boys, maybe because I had a bunch of little boys, and little boys act like electrons sometimes. Kind of unpredictable and squirrely, right? They don't stay in one place very long. So I'm just going to call the electrons little boy. So little boy going to Disneyland, he needs money, right? Let's just say it's $100 to get in. I think it's probably more than that now, but $100 to get in. So if this little kid has $75 and he goes and wants to get into Disneyland, will they let him in? No. Well, can I come in for 3/4 of a day? No. This is the entry fee. You enter or you don't, right? So that's the binding energy. Photon comes in with 3/4 of enough energy, no electrons get ejected. If the little boy comes with $100 exactly, will they let him in? Yes, they will. He's used up all his money, right? Now he has no energy, no money left. So if that photon coming in has just the threshold frequency, just the right amount of energy, it will eject the electron, but the electron's not really going to have any kinetic energy. What if the little boy has $200? Are they going to let him in? Sure. They're going to take $100 and they're going to let him in, and now he has $100 he can spend on stuff at Disneyland. He could maybe get some French fries and a soda for $100. Yeah.
Can I imagine it like you're throwing a baseball, and depending on how hard you throw it, it's gonna like go through the wall? Or is that not matching up to how this works?
I'm not seeing it. Yeah.
Not the same energy? Because the energy is in the proton?
Well, what's different about, we're talking about throwing a baseball and going through the wall or not. I suppose if you were like breaking a window, if it had enough speed, it could break the window, and if it had less speed, it would just bounce off.
But it's speed, not energy?
Well, speed is energy, right? Kinetic energy, 1/2 mv squared. So the velocity of an object is related to its energy. So the faster the ball comes, the more energy it has. If you had two balls, one small and one big, one light and one heavy, and they're moving at the same speed, the heavy ball has more energy. If they're coming at the same speed. Yeah, I think there is something there. Yeah.
I just wanted to know if, because you were using the money example,
Mm-hmm.
and I was like trying to compare it to energy.
Yeah. Yeah, so if you're, thinking of, say, a baseball, the speed at which it is thrown is related to its energy. So if you throw it fast enough, which you could think of as throwing hard or throwing easy, that's going to affect the speed, which is the energy of the ball. Yeah. So little boy goes to Disneyland with more than enough money. He pays the entrance fee, and then he has leftover money that he can spend on stuff, right? So with the photons and the electron, you get the higher energy photon. It has enough to break the electron loose, and then what happens to the extra energy? Well, the electron takes it along. He absorbs all of it, and he goes, and now he has more kinetic energy when he leaves. Any questions? So the idea of this photoelectric effect is it demonstrates that light is acting like a particle, because waves do not behave like this. Suppose a metal will eject electrons from its surface when struck by yellow light. What will happen if the surface is struck with ultraviolet light? Well, without drawing our whole diagram, which is more energetic, ultraviolet light or yellow light? Ultraviolet, right? So this is higher energy than the yellow. So yellow light has just enough energy to meet that binding energy to break it loose, to get into Disneyland. And the ultraviolet light is coming with more. What's going to happen? No electrons are ejected. Electrons will be ejected, they'll have the same kinetic energy, they'll have greater kinetic energy, or lower kinetic energy than the yellow light. So the yellow light has the $100 to get into Disneyland. The ultraviolet light has $200. So it loses $100 to the binding energy, and now it's got more, it still has energy left. Still has money left. So we will have electrons being ejected, and they'll have greater kinetic energy. These things are challenging to think about. So sometimes light behaves like a wave, the double slit experiment. At other times it seems to act like a particle, the photoelectric effect, and which behavior you observe depends on the experiment.